this video, we are going to talk about the answer to a couple of the homework questions. So we're going to discuss the relationship between mass and energy and how mass can be arranged in different configurations to either store energy or release energy. So let's start by the laws of thermodynamics. And the first law is energy is not created or destroyed. So this means that the energy we have in a system is going to stay constant regardless of the reactions that are happening. Although, by the second law of thermodynamics, some energy is lost as disorder. So when we're going through a process, not all the energy initially available is going to be available at the end, because some of that energy is lost as entropy. And so let's look at the equation for cellular respiration. And we can see in this equation that the atoms that are present at the beginning or in the reactants are also present in the products of this reaction. So the mass hasn't changed between the reactants and the products. So we have the same atoms at the beginning of the reaction as we have as outcomes of the reaction. On the other hand, we said energy is not created or destroyed. So one of the things that are happening is that we're going we're transferring energy from one molecule to another. So here, for example, we have a high energy molecule as the glucose molecule, and we're transferring that energy now to a high energy molecule as ATP. So it is very important to note that in this transfer of energy, the mass hasn't changed. So notice again, the mass in the reactants is the same mass and the same number of atoms as we have in the products. So mass has not been created or destroyed. One thing we do have extra now is this heat being produced here. So heat is a form of energy, and this heat is just the result of the second law of thermodynamics. So it says some energy is lost as disorder. So we have that disorder in biological systems is mostly heat that is being produced by the reaction. And so people tend to think that mass turns into heat, and then when we lose weight, we're losing it as heat. That is not possible because mass is not created or destroyed. Energy is not created or destroyed. Heat is a form of energy. You can use mass to store energy, but you cannot turn mass into energy. So when we look at this equation, in reality, we have two different reactions going on. So on one hand, we have the reaction of oxidizing glucose and converting it into CO2 and water. And on the other hand, we have the reaction of taking ADP and inorganic phosphate and making ATP from there. So we have two reactions. Let's look at them. So here is the reaction of oxidizing glucose, and we're turning glucose into ATP. So which of these has more energy? The reactants, in this case, glucose and oxygen, or CO2 and water? Find that glucose has more energy, right? If you're going to drink something, for example, before you run a marathon, would you rather drink a glass of syrupy glucose or a glass of carbonated water? If you look at the label in carbonated water, it has 0 calories. On the other hand, if you look at a container with high glucose syrup, for example, high fructose corn syrup is half glucose and half fructose, and it has a lot of calories, right? The sugar in your soda is mostly glucose, or even table sugar is also half glucose and half fructose. So the sugar is the one that has the calories, while water and CO2 have no calories. Oxygen doesn't really have calories, but oxygen is necessary for the reaction to happen as the electron acceptor. So we have a reaction where we go from high energy reactants to low energy products. This is what we call an exergonic reaction. And in this, energy is released. So we have a decrease in free energy. We have a negative delta G. So this is energy at the beginning in the reactants was higher than the energy at the end. So the overall energy in the system decreased as the reaction progressed, and we ended with low energy products. On the other hand, in ATP synthesis, we start in our reactants are ADP and phosphate, and these are lower energy compared to ATP. So we start with low energy reactants here, and we start with low energy reactants and we move to high energy products. So in this case, we have an endergonic reaction, so energy is going into the system. We have an increase in energy, so we have a positive delta G, and energy had to be supplied. So this is like rolling uphill. So if we're going from low energy reactants to high energy products, that energy has to come from somewhere. And that's a gain in energy, but that energy has to be supplied by some other reaction. So an important message here is that the law of thermodynamics tells us energy is not created or destroyed. And following the conservation of mass, mass is also not created or destroyed. So we have here the energy that is present in the reactants is also going to be present in the products, although some of it is lost as heat. And the mass that is present in the reactants is the same mass as we have in the products. So just like batteries, whether they're fully charged or low charged, they will still weigh the same. A way to think of it, an analogy I like to use is the analogy of using magnets. So for example, if you have two magnets and you place them facing the opposite poles to each other, you'll find that the opposite poles attract. So the magnets will quickly want to bind together. So this will be a bond that will be very easy to form. But on the other hand, if you try to separate those magnets, you're going to have to put energy into separate them, because now they want to be stuck together. So this will be an example of an endergonic reaction, where exergonic reaction, but it's very easy for it to happen. But on the other hand, if you want to reverse that, now you have to. The same magnets you can now assemble having the same poles facing each other. So now when the poles are facing each other, it will be very difficult to put them together because the magnets repel each other. But on the other hand, as soon as you let them go, the magnets will move apart, and that will release energy. So this is an example of a bond that contains energy, took energy to form it, but to separate it, it will release energy. This is a good analogy for how ATP works. So ATP has three phosphates together, and phosphates, to join them together, those are very high energy bonds. And the reason why energy bonds is because phosphates are very negative. Phosphates have not just a phosphate atom, but this oxygen that is highly negative. So it's like putting three negative magnets together that they want to repel each other. Putting them together takes energy, but once you separate them, they release energy. So we already discussed how ATP synthesis is an endergonic reaction in which it takes energy to go from ADP and phosphate to forming ATP. So what do you think is going to be the opposite reaction, in which we break down ATP into ADP and phosphate? And what you have is high energy reactants now and low energy products. So in this case, breaking down ATP is a reaction that releases energy. Bringing this back to the question of where is the mass in the compost pile going, we can come back again to this equation. So we already talked how the mass in the reactants is the same mass as we're going to have in the products, but now the mass that was in glucose and glucose and oxygen is now CO2 and water. So the mass hasn't changed. However, glucose, while it is a solid liquid substance, CO2 on the other hand is a gas. So it is evaporating into the atmosphere, the mass still there, but it's now a gas that we just don't see with our eyes. And the energy now that was in the glucose molecule has been used by microorganisms to make ATP, and by the second law of thermodynamics, some of that energy was lost as heat. So the energy was used for making ATP, and some of it was lost to the entropy or heat. So here we have the leaves decomposing, microorganisms are eating them, so some of the mass is also going into the microorganisms as they grow, and they're using that glucose for making ATP. In the process, they're using the energy in the glucose to make ATP. In the process, the glucose is being converted to CO2 and water, which simply evaporates. So we see the amount of leaves decreasing, but it's because they're literally evaporating by the action of respiration. And the energy in the glucose molecule is now transferred into ATP that the microorganisms use for their regular activities, and heat. So if you look at it, if you feel the temperature of the leaves is also increasing because of that entropy.